Okay, so good morning, everyone. Welcome to day 2 of the workshop. And I'm very excited today to be teaching you about the nuts and bolts of MCell and our user interface to it called Cell Blender, and our new user interface to it implemented in Python. And some of you may have been familiar with MCell from before and Cell Blender from before. Things are going to be mostly the same on the surface, but I'm not going to point out the differences too much because many of you haven't seen it before, and so why confuse you with how things used to be done? We're just going to dive right into how things are currently done, and I might lapse into the past a little bit here and there, but but to get started, let me share my screen and get you started with a lecture about how to build a synapse with MCell and Cell Blender. And Terry likes to point out that these tools together create what he likes to call a computational microscope for spatially realistic simulation of cellular microphysiology. And before we get into things very deeply, we're going to go all the way super deep to the concept that scientific computing enables the scientific discovery cycle. And in the scientific discovery cycle, we make observations about the world, and from these observations, we kind of make, predictions in our heads about how things work, and that leads to a formal hypothesis, which can be tested with experiments if you can design the experiment to test your prediction. And then, of course, the result of the experiment leads to more observations. And if we can keep going around and around this loop, we continue to create, make scientific discoveries about how the world works. And of course, our hypotheses have to be falsifiable to be scientifically useful. And the experiment decides between the truth or false or incorrectness of our hypothesis. But what happens when the system that we're trying to discover is so complicated we can't think about it? Well, this is a big problem because hypotheses are a human intellect in your mind process. And over here in the types of models that we can perform, types of experiments and types of models that we can perform, at the very top of this pyramid here, I put thought experiments, mental models, which operate on mental models. Without these, you can make no hypotheses. And the scientific discovery cycle would grind to a halt. And of course, because we have to come up with experiments, and the experiments have to be done on the physical world somehow, so that we can figure things out. But what if we could make computational experiments? Let's see. Right here, no. Okay, computational experiments. And with computational experiments, we have ultimate control over all the pieces that we put together. It's kind of like a toy. It's an extension of the thought process. We can take our thoughts and our ideas and instantiate them in the form of a computational model that we can then play with. And from this, maybe we can make more observations about the behavior of our computational model and tune our intuition to be able to formulate a more intelligent experiment or something that we could possibly do in the physical world again to keep things going. And this is really at the core of, I think, of what Richard Feynman was getting at when he said, what I cannot create, I do not understand. And here the creation is in the form of a computational experiment that you can create that can then help you, make discoveries about the physical world in experiments that you can create. And philosophically, this leads to a statement about our approach, which is understanding through simulation. So this was the motivation behind our original creation of MCell back when I was doing my PhD thesis work at Cornell University. Our question was, how do synapses work? And how does synaptic structure influence synaptic function? And my work there was on the neuromuscular junction, but when I joined Terry's lab, the goal was to take what we had learned about the neuromuscular junction and apply it to synapses of the central nervous system. And this brings us into synapses that are embedded and driven by axons and the synaptic contacts in the neural pill of the brain. And the neural pill is this incredibly dense structure that's just frightening. That's why I put 3 exclamation points here. It's just frightening in its complexity. And then how does the organization of pre and postsynaptic cytoplasmic organelles influence or give rise to the behavior of synapses? And we have to know about the distributions of receptors, ion channels, enzymes, and transporters within the structure, because the spatial organization of it is so important. And also, of course, within that space, we have all the biochemical reaction networks. So we have networks upon networks. We have networks of cells, neurons, networks of membranous compartments, networks of receptors and ion channels that are carrying out networks of reactions, and all within a spatially diverse and very heterogeneous makeup and dynamics that are localized. And because the dynamics are localized, then we can't think of cells as well-mixed bags of soup, right? And so, and the compartments are so small that the numbers of molecules and ions within these compartments that are carrying these things out, the numbers are so small that we must include the stochastic spatial temporal dynamics. And from all this, me and my colleagues invented MCell as a way for us to approach these questions computationally, to try to beat back the complexity and make models that are simpler, so that we can play with them as a child plays with toys when they're infants and growing up learning. So what is MCell? Well, MCell is a Monte Carlo simulator of cellular microphysiology. It models realistic 3D reaction diffusion systems, and it's implemented using rigorously validated and highly optimized stochastic Monte Carlo methods that we've developed over many years, starting with what I was taught by my colleague, my mentor, Mika Salpeter, and her husband, Ed Salpeter, at Cornell University. It tracks the Brownian dynamics diffusion and reaction of individual particles in 3D and on 2D surfaces embedded in 3D. And in arbitrarily complex 3D geometry made from triangulated surfaces. And because it's in 3D, this makes things very much more difficult. And so we need to have tools that help us create and validate and control these surfaces. And so a lot of what we do uses, excellent software that comes from maturing and excellent software that's coming to us from the computer graphics industry and academic pursuits. And you learned yesterday from Jim about how the BioNetGen language can be used to describe arbitrarily complex reaction networks. And thanks to the network-free rule-based specifications that Jim talked about yesterday, we can really say arbitrarily complex, because the rule-based specification lets us pretty effectively beat back the curse of the combinatorial explosion that that exists in these reaction pathways. And in MCell, we can treat these as classic Markov processes or rule-based specifications, as you learned yesterday. And these are modeled as discrete event-driven point processes, as you'll see, rather than as populations of particles interacting. And all of this power is harnessed using a flexible and powerful Python API that's new now. And this workshop, today is the first time we've ever taught this Python API to a class. So this is a brand new enhancement and milestone that we've been able to achieve with the effort of our whole excellent team that we have. And also there's a sophisticated model building, visualization, and analysis environment that can be used to create the models called Cell Blender, which is based on the computer graphics tool called Blender that I was alluding to. Up here, Blender lets us create and visualize and control and understand the 3D organization and 3D structure of the models that we're trying to put together. Okay, so that's what this describes MCell. Let's get into the nuts and bolts of how MCell works.
Sorry, Tom, I was wondering, can you put the slides on full screen?
Well, I'm having, since I have two monitors,
okay.
I have some trouble with that. But I wish I could make this wider over here so that I don't have, okay, I can kind of center that a little bit better. Yeah, I apologize for that, but I don't know why PowerPoint and Keynote are so lame at letting me say where I want the display to be. Well, actually, maybe there is. I think earlier I tried to. Yeah. Let me try this. Let me try this. This might work. If I say arrange and mirror. Okay, then I get a mirror of everything. And let's see, so that works. I can get rid of that. Get rid of that. Are you still seeing everything okay?
Yes.
Yeah, okay. And then I should be able to, where's my mouse? There it is, okay. I lost my mouse for a second there. I should be able to say play on this Mac. How's that?
Oh, perfect, thank you.
Okay, but can you see the thumbnail of all your pictures or no? Or is Zoom not showing that? I don't want Zoom to show that.
No, just the slide.
No, okay, just the slide. Okay, good.
Thank you.
Okay, so everything starts in reaction diffusion systems. Everything starts with the diffusion. You learned about reactions yesterday, but let's talk about diffusion, and then we'll get back into the reactions how we implement them in among diffusing particles in a few slides. So the way we can look at diffusion, there's kind of two different ways we could look at diffusion of particles. We could use the molecular dynamics Newtonian mechanics approach, or we can use a statistical mechanics approach. So in the statistical mechanical view, particles have a thermal velocity given approximately by this equation, square root of 3 kT over m, where k is Boltzmann's constant, t is temperature, m is the mass of the particle. And for water, if we fill in these values at say room temperature, we get that the velocity of water molecules in liquid water, because this temperature is liquid water, the velocity is about 640 meters per second, which incidentally, and not by any random occurrence, is approximately the speed of sound in water. And that's a clue for what we're going to talk about next. Okay, so the water's going 640 meters per second. Why don't we explode? Well, the reason we don't explode is because the particles don't get very far between collisions, and their energy, the energies of the collisions, is so small that that the temperature doesn't go up. In fact, the reason they're moving is because of the temperature, right? So they're not making any extra heat when they're colliding with each other. That is the heat of their collisions. That is what it's coming from. That's what it means to have thermal velocity, okay? But how far do the water molecules go between collisions? This is just a quick and dirty back of the envelope kind of way of calculating it. This isn't a real formal accounting of everything, but it's a pretty good approximation. So we start with the density of water, the molecular weight of water, the molarity of water, and this tells us then how many molecules of water there are in a cubic centimeter of water. And then from that, we can calculate what's the average volume surrounding each water molecule. Of course, the water molecules themselves are two hydrogens and an oxygen, and we can get their Bohr, the Bohr radius of all those things and the molecular size of that whole thing. But what this calculation here is kind of the average volume around each molecule. And let's assume that each molecule's environment or neighborhood corresponds to a spherical space. Then the radius of that little sphere would be about 0.2 nanometers. And at 640 meters per second, this would mean that it would only take about 0.3 picoseconds for the one water molecule to move and collide with its neighbor, 300 femtoseconds. Okay, and we could simulate all this behavior using a molecular dynamics approach. And if we did, the time step of that simulation would have to be finer than about 300 picoseconds if we wanted to really capture what was going on. Okay, 300 femtoseconds, I meant to say. 0.3 picoseconds is 300 femtoseconds. And it turns out that in most molecular dynamics simulations that people do, they have a time step on the order of femtoseconds, or a few tens of femtoseconds. So that's at the temperatures we're talking about and the densities of particles we're talking about in biological systems, that the densest thing in there is the water itself. 55 moles per liter is the concentration of water in water. So in that aqueous environment, to do molecular dynamic simulations, most of the thing that is constraining the time step of your simulation are the motions of the molecules at that temperature, and so it's in the femtosecond time scale range. And but let's look at this from the point of view of statistical mechanics and the fixed laws of diffusion, also closely examined by Albert Einstein at the turn of the 19th century, 20th century. And specifically Fick's second law can be used to describe the statistical mechanical motions of populations or regions of space containing molecules. And Fick's second law applies when the concentration in the volume of some particle is changing in time, meaning that the flux into the system is not equal to the flux out of the system. And that's if that's true, then Fick's second law is what you want to use, and can be expressed like this: that the rate of change, the partial derivative of the rate of change of concentration in time, is given by the square of the gradient times the constant of the concentration times some scaling factor called d, which is the diffusion constant. And in free space, if I start with a point source of particles, we can solve that differential equation, partial differential equation, to get the rate of change of density with radius and time of the particles in our system. And if we generalize the solution to this in d dimensions, in little d dimensions, where you can just fill in 1 for one-dimensional diffusion, 2 for two-dimensional diffusion, or 3 for three-dimensional diffusion, you get this generalized equation for describing that density in radius and time. And we can parameterize this equation according to a dimensionless scaling factor called, a length constant scaling factor called lambda, which is square root of 4 dt. And if we look at the solution to this equation and divide through by lambda to turn our radius into a dimensionless radius, r tilde, then we can solve this. Then we can plot this equation in this dimensionless space, r tilde, and what we get is this density function looks like this light gray curve here, the area under this light gray curve. And r tilde is the dimensionless radius factor. And it's dimensionless because radius is a length and lambda is a length. So r tilde is a dimensionless radius. And if we take the cumulative distribution function of this solution, I don't have the equation for that written here, but the cumulative distribution function of that looks like this this dark black curve here. And what's great about making cumulative distribution functions in Monte Carlo sampling, in Monte Carlo simulation, is that after you have this cumulative distribution function that goes from 0 to 1, you can use a uniform random number generator that generates uniform random numbers on the interval between 0 and 1, and use those values to pick off values of r tilde, like this. And this is the basis for how we can use a random number generator to sample any shaped distribution and get a reconstruction of that probability distribution function. So this sampling technique is sometimes called slice Monte Carlo sampling, and it's at the basis of the famous Metropolis Monte Carlo algorithm that was invented by physicists and mathematicians during the Manhattan Project to understand nuclear fission and critical mass. And if we take this function, so important for slides coming up later, in a few slides from now, if we take this solution and calculate the expectation value or the average of the radial distance at of basically r, the average length that particles move, we get this answer, which is 2 times the square root of 4d delta t over pi. And you might ask, well, why didn't I factor out the 2s and 4s and everything? It's because I wanted to keep the connection back to lambda 4d delta t, so that you can see that lambda, where lambda still sits in this equation. And the reason why the 4 isn't factored out here is because in the textbooks on diffusion, you'll always see lambda written as square root of 4d delta t over pi, not 2 times the square root of 4d delta t. And so the average radial diffusion distance that particles will move is this quantity here. And the average distance that particles move normal to a reference plane, I mean, along the direction of a normal to any plane that you define. And this is going to be important for development of the algorithms in a few slides from now. This distance is just half of the radial distance. So instead of 2 times, it's just 1 times square root of 4d delta t over pi. Okay. And what I'm showing you here, these values correspond to 3-dimensional diffusion. And I should have put up here in 3 dimensions. This is how things look if we put little 3 here for little d. Okay. So that gives us a randomly sampled distribution of distances that the particles will move in our simulation, in our random walk simulation that we're going to do. And we also need to sample random directions. And we have to sample the random directions without any bias. So that means sampling the surface of a sphere at points of equal area. And what you're seeing here is 1 octant of a sphere sampled in such a way that every little a point on here is sampling a neighborhood of area equal to all the other points in here. And then to eliminate any bias, we take this octant and replicate it, 8 times to get or 7 more times to get the full sphere. And because this 1 octant is unbiased, then the entire sphere will be unbiased. And it's really important to sample without any bias, because if even the tiniest amount of asymmetry in sampling the random walk will produce over millions of time steps. If there's any tiny bias, that bias will be added up 1,000,000 times and amplified by a factor of 1,000,000 after 1,000,000 time steps. So yeah, it's really important to guarantee that you have no bias in the sampling. Okay, so what these 2 things give us, sampling this and sampling this, what they give us is what we call a grid-free random walk. So our random walk is not walking on a large scale lattice, like you might see in some random walk implementations. Instead, these are random walking on at the granularity of double precision floating point numbers. So there is a grid, but the grid is the grid of double precision floating point numbers. So as fine as as fine as we can reasonably do and efficiently do in the computer. And what we get, the benefit of this is illustrated here. So here we're showing in 3D again, and then on the left here in 2 dimensions, the solutions to the analytic diffusion equation. So this curve here is exactly, this curve for 3D. And you can see for 2D, the shape of the curve is slightly different. So the black line is the analytic solution to the diffusion equation. And if we take just, 100 1 microsecond time steps, say, then we get the little black dots and we have I can't remember how many particles we were using to diffuse here. So the noise here is due to the finite number of particles in the system that we were simulating. If we increase that number of particles, then we would get closer and closer to this line. But you can see, the black dots very, very nicely, sample and approximate the analytic solution. But what's cool is about the grid-free random walk method that we've implemented, even after a single time step of 100 microseconds, which should be an equal delta t to 100 times 1 microsecond. Even after a single time step, we still can recover the shape of the analytic solution. So even a single time step reproduces the shape of the probability distribution function that we're trying to do. And this is what happens when you do Monte Carlo sampling of cumulative distribution functions. That's what you get. So it's really a beautiful, elegant thing. And of course, in 2D, we also can validate and verify that we get the right answer. Okay. So that's how our random walk diffusion works in unbounded 3D space. But now let's talk about how we are going to represent the surfaces, the boundaries, the interfaces, the scaffolds, etc., that are going to make up our computational reaction diffusion method. So the way we represent surfaces in MCell and many other computer graphics systems is using what's called a triangle mesh. So the basic element of the triangle mesh is a triangle mesh element, a single mesh element, which is composed of 3 vertices numbered 0, 1, and 2. And if you use the right-hand rule from physics to wrap the fingers of your right hand in the direction of the connectivity between the vertices in your triangle, your thumb will point in the direction of the normal vector of that surface. And you can see that if I reverse the ordering, say of 1 and 2, so if this is 0, 1, 2, and if I wrap my fingers in that way, my thumb would point in the opposite direction. So this gives us a well-defined way of determining the front face of a mesh element and the back face of a mesh element. And the whole surface is made up of a grid, an array of mesh elements that are all connected together. And they're connected together in such a way that the next triangle over will share 2 vertices with the first triangle and will share 1 edge between them. So if the mesh is a manifold mesh, meaning it's a mesh that if it were true that if I had a mesh say of a sphere-shaped object, and if every mesh element, if every triangle in the mesh, or if every edge, if we look at it the other way, if every edge in our mesh is shared by exactly 2 triangles, and not 1 triangle and not 3 triangles, if every edge is shared by exactly 2 triangles in our mesh, we will have what's called a manifold mesh. And that means it has a well-defined interior and exterior. But from the point of view of determining whether we're inside or outside, it's important that that all the normal vectors of our surface have to be consistently oriented. So, for example, what if I had another triangle over here, where this is numbered, 0, 1, 3? What if vertex number 3 were over here? And what if I connected to the vertices together in the order 0, 1, 3? If I did that, and if this one was 0, 1, 2, 0, 1, 2 says the normal vector is pointing this way, but 0, 1, 3, if you use the right-hand rule, says that the normal vector would be pointing inward, right? And so that would be inconsistent orientations of the normal vectors. And even though the whole mesh might be fully closed, and visually you're looking at it, it says, oh, there's the inside and there's the outside. Visually you look at it. Mathematically, the computer is looking at the orders of the connectivity of the mesh elements. And mathematically, with inconsistently oriented normal vectors, the computer wouldn't be able to find a consistent interior and exterior for that object. That well-defined interior and exterior comes from the consistent orientations of the normal vectors. Okay. And this is a good reason for using a 3D computer graphics system that is very robust, because it can, that system can repair or guarantee that your meshes that you're creating for your model do satisfy this condition. Okay, so that's how we represent boundaries. How do we represent diffusion with those boundaries? Okay, so over here in panel A is the 3D case, and B shows the surface diffusion case. So let's talk about bounded volume diffusion. If we look at one of our triangle elements in side view, that's shown here in this hashed area, that's one of our triangles, and we're looking at it exactly on edge. Then if I have a particle, say, of A that's inside the surface, or toward the back side of the triangle, if that molecule of A diffuses with a certain distance and a certain direction, it might end up here, say, up here. Its trajectory can be calculated by what's called a line plane intersection test to calculate where the point of collision is between this vector and this polygon. And what we do is calculate the angle of incidence and make an angle of reflection that's equal to that angle of incidence, and then preserve the path length of the particle. So the total path length of the particle that it would have taken if the surface weren't there is preserved. All we've done is bent it by what a process called specular reflection, meaning a mirror-like reflection. And so it's being mirror-like, then this position here is just reflected back down here as if it were viewed through a mirror. And what this does mathematically to our probability distribution function that we were trying to preserve back here and calculate so carefully here, all we've done to that probability distribution function is make a mirror image of it, and that changes only the region of space occupied by the molecules, but it does not distort one bit the density function that we're trying to sample. And all we've done is take whatever density of particles that might have existed up here. If the surface weren't there, we just take that and reflect it down and project it down on top of itself. And it can be shown that that does not distort the shape of our probability distribution function. And then we do something similar in 2D for molecules diffusing in the surface. Say this is, let's say these are two neighboring triangles in our surface, and we have an edge. So in 3D, a boundary is a triangle. And in 2D, a boundary is a line. Okay, so that's an interesting fact of the dimensionality reduction, that a 3D surface is made up, you know, a three-dimensional shape has a boundary made up of two-dimensional elements, and a two-dimensional space is made up of boundaries that are one dimensional. And so our boundary is a line, and so instead of doing an intersection of 3D diffusion with a triangle, we do 2D diffusion intersecting with a line, and we can make reflections about that line, similar to what we did here. But one important difference is that these two triangles might have a dihedral angle between them, and so we have to bend. It's hard to see here in this picture because it's a two-dimensional projection of this is a projection of a three-dimensional thing onto a two-dimensional thing, and then I'm showing you one-dimensional you know, intersections here. Anyway, we have to bend this line so that it still lies. So this line here that lies in this plane, in the plane of this triangle, has to be bent so that after it passes through, it lies in the plane of this triangle. Okay. Okay, so now we have seen how we're going to handle random walk diffusion and collisions with boundaries. We're now ready to talk about how we're going to handle biochemical reactions. So yesterday, you know, Jim gave a great explanation for you know, sampling the first order decay lifetimes of you know, molecules undergoing unimolecular reactions with rate K. And here I'm just stating again things that, you know, that Jim talked about yesterday. So the distribution of first order decay lifetimes is given by Ke to the minus Kt. And if we sample this with a random number generator to sample a lifetime of a single particle with undergoing this process, we can write this down this way. R is a uniform random variate between 0 and 1, and so if we take minus the natural log of that number divided by K, that will give us one sample of a T sub L lifetime of a single particle in the population undergoing this process. So this is how we, this is the very simple way that we do this in MCell. And this lifetime is then used to put the molecule into a scheduler. And let's say at the beginning of the simulation, a molecule A, let's say we write down, you know, in our simulation, we write down this reaction A goes to B with rate K, and we say we want, you know, 100 A molecules to start off in our simulation. So at the beginning of the simulation, during initialization, 100 molecules of A will be placed into the simulation. And at the moment they come into existence, at the beginning of the simulation, MCell looks at the set of reactions that says, oh, you have a reaction that says A goes to B with rate K. So these A molecules aren't going to live forever in your simulation. So at the moment they come into existence, MCell says, ah, there's a rate K. for those, and it's a unimolecular reaction. So what it does is for each molecule of A, it samples this and calculates a lifetime for those A molecules and gives them a lifetime and schedules that lifetime into a event-driven scheduler. And the event that's going to drive the A molecules is their lifetime. And so MCell will say, let things occur up till each molecule's lifetime, and when its lifetime has come up, if nothing else has happened to the molecule, between time 0 and time T sub L for a given molecule, at the moment T sub L occurs, then MCell will say, okay, it's time for that molecule of A to become a molecule of B, or be destroyed, and a molecule of B is created in its place. And if molecule B had a reaction, at the moment a molecule of B is created into the simulation, the lifetime of each B molecule would be calculated and put into the scheduler. So MCell is going from event to event by looking at events in the scheduler and picking off the events as they come due and handling the events as they come due. Okay, so that's unimolecular reaction. Now, what about bimolecular reactions where we say A plus B goes to C with rate K? So here we can't calculate the lifetime of A and B individually. Well, you could if you were using the Gillespie algorithm, but the Gillespie algorithm, the stochastic simulation algorithm, SSA algorithm, invented by Gillespie, treats the molecules of A and B not as individuals, but as populations. So if you have the population, then you can calculate the time of the next reaction within the population. But in MCell, we're not treating A and B as populations. We're treating them as individual, discrete, random walking entities. And so what we do here, instead of calculating the propensity for A and B to become C across the whole population, we calculate it individually based on the collisions between individual A and B molecules. So because we don't know when the particles might collide, we can't calculate a lifetime a priori. So we have to do what's called collision detection to calculate the collisions between A and B. Okay, so in this diagram, we're gonna say, what if the B molecule is on a surface? And how do we treat molecules on a surface in MCell? Well, a surface is made of triangles. Here's one triangle of the surface. And we could subdivide that triangle into subtriangles using a process called barycentric subdivision, where we divide the triangle up into an integer number, cut the edge of each triangle into an integer number of cuts. And this produces a barycentric grid, and creating little tiles, little triangle tiles that are self-similar to the triangle that they live on. We call these effector tiles, ETs. So the area of an effector tile is A sub ET. And if we imagine above this triangle extruding a prism whose shape is equal to the footprint, and the height of the prism is equal to this quantity we showed earlier, L bar perpendicular along the normal vector, in the direction of the normal vector, this creates a little volume, a volume that's whose computed volume is A sub ET times the length of the normal vector. I mean, the average step length along the normal vector. And if we have molecules, so let's imagine that this effector tile represents a single molecule of B, and the molecules of A in the volume that are possibly going to react with and with molecules of B let's calculate how many molecules of A are inside this prism. Well, that's just going to be Avogadro's number times the height of the prism times the base of the prism times the concentration of A molecules. So this gives us the number of molecules of A that are inside this prism. Okay. And so in a single time step, remember this L bar perpendicular quantity here is the average diffusion step length that the particles will take in a single time step, average length normal to the surface. So in a single time step, these molecules of A will have a chance to hit the B molecule. And so that's what we call the number of hits, n sub h. And this is on one side of the surface. We can imagine that there's another prism like this below, and particles below will come up and hit from below. But let's just talk about from one side of the surface. This is the number of hits that occur. Okay. So now, what we want to be able to calculate is what's the probability of reaction between the diffusing volume molecules and a single surface molecule. Okay, so what we've described here is our diffusing volume molecules reacting with a single surface molecule. From mass, let's define the probability of reaction, PBT. This is the probability of binding over time delta T for all the molecules of A reacting with a single molecule of B. So because we're talking about reaction with a single molecule of B, we have divided, K times concentration A times concentration of B. We've divided by the concentration of B, so we're talking about a single molecule of B. So we just get K concentration of A times delta T. So for mass action kinetics, this is the probability that our concentration of A molecules in our little volume will react in time delta T and bind to our single molecule of B. So that's why this is a probability of reaction. It's a probability of reaction to that a single molecule of B will be bound after time delta T. Okay, now we can calculate this same quantity, PBT, but from the point of view of rate of encounter. So this is mass action kinetics over here, but from the point of view of Smolakowski rate of encounter from the Einstein-Smolakowski equation. So what I just described over here, this picture is kind of a simple diagrammatic way of computing what was derived by Albert Einstein and Marian Smolakowski back in the early 1900s to get what's called the rate of encounter or the number of hits. Okay, so from the rate of encounter, we can calculate the probability of our B molecule being bound by the collection of A molecules colliding with it, this way. So let's say there's a probability of binding between a single molecule of A and a single molecule of B, PB. And we don't know what PB is, but this is the probability that when a single molecule of A hits a single molecule of B, that there'll be a binding between them. And we don't know what this is, but let's just define it, PB. So PB is a probability that it's bound after a single collision, and 1 minus PB is a probability that's not bound after the single collision. And so then 1 minus PB to the n sub h power is the probability that it's still not bound after that our B molecule is still not bound after being hit n sub h times. Okay, these are all this is a single molecule A hitting B, and then this is all the molecules of A and our little prism colliding with our molecule of B. So 1 minus PB to the n sub h power probability that it's not bound, the B molecule is not bound after being hit n sub h times. And then 1 minus that is the probability that it is bound after being hit n sub h times. So that's our PBT, the probability that it is bound after being hit n sub h times. Now, fortunately, this is a complicated equation because there's a exponent here, but we can simplify it by making the assumption, the simplifying assumption that if n sub h is small and PB is small, and this will be true if our time step is small, then this whole thing is approximately equal to n sub h times PB. Okay, so this is PBT, n sub h times PB. So that means n sub h times PB is equal to K times the concentration of A times delta T. So, okay, so let's expand n sub h. It's this. So this is really Avogadro's number times the height of the prism, the area of the base of the prism, concentration of A times PB, right here. If we expanded this whole equation out, and now let's rearrange and solve for PB, because this is the thing that we don't know the value for. This is the thing that we really like to know, because in MCell we're calculating the motions of individual molecules and the collisions between individual molecules. So when a single A molecule hits a single B molecule with rate K, what's the probability that that single collision should result in the formation of C? Okay, so if we do that, we can see really interestingly that the concentration of A on the left side of the equation cancels the concentration of A on the right side of the equation. And so this gives us a result that is intuitively makes sense, that a single molecule of A and a single molecule of B colliding with each other, there's no defined concentration for that concept, right? These are single collisions, and the probability of binding of a single A and a single B molecule shouldn't depend on the concentration of all the other A molecules in the solution. This is an individual event that's happening. And so the concept of concentration shouldn't matter, and it doesn't, right? So concentration A drops out of the equation, and we get this, this fundamental equation that we use in MCell. So the probability of binding of between a single A and a single B is equal to the rate constant K divided by Avogadro's number and the area of the triangle times the square root of pi delta T over D. So what this is saying is that the probability for a given K that we want to have happen, as the particles move faster, if diffusion constant is higher, intuitively, this means that there's going to be more collisions. Collisions are going to happen more often, then the probability should be less. Because we have more collisions, the probability per collision should be less to get the value of K that I've asked for in my simulation. Also, this says that the longer the time step is, the larger the probability should be. Now that's weird, because a longer time step, that should also mean more collisions, right? But actually, because of the way diffusion, the way the random walk algorithm scales, when we make the time step longer, the particles are treated as moving in a straight line between time t0 and time t, time t1 and time n and n plus 1, or time 0 and time 1. So MCell treats, the random walk algorithm treats that trajectory over time delta t as a straight line, whereas in fact, if we went to a finer time steps all the way down to the molecular dynamics time step, the path of the particle between point A and point B on a finer time scale is actually a tortuous long path. And so there would actually be more collisions occurring on the finer time step over time delta t than we're actually accounting for over our sampled longer delta t. And so this is why, and that number of collisions scales as the square root of t. So to compensate for that, that's why this goes as square root of delta T. And the other thing that we learned here is that the area of the effector tiles, the larger the effector tile is, the smaller PB should be. And this makes sense because if the effector tile was larger, there'd be more collisions with it. And so the probability of binding per collision should be less in order to get the K that we want. Okay. Now, an important point to make here is that PB is a probability, and it needs to be a value between 0 and 1. And notice that there's nothing in this equation that keeps PB from being greater than 1. So the only control over this is you, the person making the simulation, or the MCell algorithm, making sure that these probabilities don't exceed 1. And the control you have over it is, well, you can't K, or let's talk about this. So K is a value that that biology says is the rate constant for the binding, for the reaction. So you can't control K. Nature controls K. If you're trying to make your simulation realistic, you need to have a realistic K, right? Obviously, you could lie and put any value of K you want, but that wouldn't be realistic. Also, the diffusion constant D is the value that nature says it should be. And AET, well, if you're trying, it's important to try to keep AET about equal to the size of your molecules. If you don't, then molecules will be too large, and their spatial locality will be kind of blurred and fuzzed out if you make AET too large. And so you need to keep AET also governed, a size governed by nature. So this means the only real control you have over PB is delta T. And we've just at the beginning of our discussion here, we said that delta T in a molecular dynamics simulation is on the femtosecond timescale. Wouldn't it be horrible if our whole approach, reason for taking the statistical mechanical approach was to try to get to longer time steps than femtoseconds by using a random walk rather than Newtonian mechanics, following every single path and every single collision in reality at the molecular dynamics scale. So wouldn't it be terrible if delta T had to be a femtosecond here in order to keep PB less than 1? But it turns out that for values of K from nature and sizes of molecules from nature and diffusion constants from nature, filling those in, the value of delta T that that typically works out to keep PB less than 1 can be on the order of a microsecond. So that is 9 orders of magnitude coarser than and faster than the femtosecond timescale used in molecular dynamics. So that's kind of a little mini miracle and good luck that we hit there. Okay, so this diagram that I showed was for diffusion between volume molecules colliding with the surface molecule. How do we handle the other kinds of reactions, bimolecular reactions that are allowed in MCell? Namely, we can have molecules between A and B can both be volume molecules, or A and B can both be surface molecules, in addition to this volume molecule interacting with surface molecule. How do we handle the other cases? Well, so for the volume case, let's start with that one. The way we handle it is just by a simple change of frame of reference. So rather than thinking of diffusing molecules hitting a surface, let's imagine a single molecule of A diffusing, and there's an imaginary interaction radius around it, and when it moves, it sweeps out a cylindrical volume. And what we are calculating is how many other particles get swept up inside that imaginary cylindrical volume as it moves. So just a change of frame of reference. But now, since we're talking about radial diffusion rather than normal to a surface, rather than using L perpendicular bar, we use LR bar from the solution to the diffusion equation that we had earlier, right? Just to rewind and remind you of that. Rather than using L perpendicular bar, we use LR bar. And that's just 2 times L perpendicular bar. So we fill in the same equation, but we replace L perpendicular bar with LR bar, and we get this, we'll calculate the same probability. Okay. Except for one subtlety that's important. With our volume surface interaction, these effector tiles, since they're on the surface, are always accessible by the diffusing molecules of A when they're diffusing. And they're always, and because we've done barycentric subdivision on each triangle, all the effector tiles are the same size on each triangle. Okay. But in the volumetric case, we're sweeping out these interaction radii and sweeping out these cylinders. Now, if the particle that we collide with is out in the middle of the volume and this cylinder is not truncated by any neighboring surface nearby, then the collision cross-section area for that, so recall that what we're calculating here is the Einstein-Shmolakowski rate of encounter, which is really dependent on the collision cross-section, right? Which is this AET. The collision cross-section out here is the full interaction radius disk area. Okay, but when a particle is on the wrong side of the surface, then we shouldn't collide with it at all. So this one should not be included in the swept out cylinder, and we make sure that it isn't. Okay, so that's easy. That makes sense. But what happens when a particle is on the right side of the surface, but is close enough to the surface so that this collision cross section is truncated like this? What we need to do is account for the fact that the collision cross section for that particle is not as big as it should be. So we're going to count fewer collisions with that particle than we should on average. Because we're counting fewer collisions with that, we need to increase the probability of binding per collision for these to compensate for the truncated area. And in MCell, we do this correctly. So there's a lot of math that's going on in the calculation of these collisions. And this is an important part of the math. Okay. Now, on the surface, we have yet another change in frame of reference. Now we're in 2D, and what we're talking about is collision with not with areas, but with lengths. And so we have a different formulation for the probability, and we look at the neighbors and calculate their probability reaction per collision based on proximity to neighbors and these lengths. And then we've already seen the volume surface case where particles move and they hit the effector tile. Okay. Okay, so that concludes kind of the nuts and bolts part of talking about how MCell works. Maybe I'll just stop here for a moment and see if there are any questions from you before I continue on to the next part. Or at least someone say something so I know that you're still connected. Because it was so quiet, Zoom could have cut me off and I could have been talking to myself that whole time. Okay, there's a thumbs up. Okay, great. Thank you.
There has been a lot. Sorry.
No,
go ahead. I mean, I wanted just to say that there has been a lot going on in the chat. I mean, it's not that
maybe I should stop and answer some questions from the chat. What do you think? How do I see the chat? Okay. I should have had the chat up. But this is the disadvantage of going to just one mirrored screen. I can't see the chat.
I personally think it's impossible to keep, to do a presentation and also answer or, be looking at the chat. But Adam, I think, kind of took care of all the questions there.
Okay, good.
There's one new question at the bottom, I believe. But everybody who asked, please, if you have some additional questions, I'm sure Tom will be happy to answer.
Yeah, sure. Well, so this last question, how is the prism length determined? Okay, so let me put that chat away over there. And where's my mouse? There it is. Okay, go back. Back up again. Hello? Why isn't that? There it goes. Okay. Okay, so I can sort of see the chat. You can't see my chat, right? The chat window.
No.
No,
okay,
just
good. Yeah, I'm just worried that it, might obscure the picture. Okay. So the height of the prism is determined by this value L perpendicular bar. The average diffusion step length that the particles take in one time step, normal along the direction of the normal to the surface. And that was determined by taking the diffusion equation, the solution to the diffusion equation, and finding what's called the expectation value of that, or the average, right? And I don't have the derivation here that walks through how to do it, but the answer is this value. So this is where it comes from. So it's square root of 4d delta t over pi. So it comes from the time step of the simulation and the diffusion constant d of your particle. So that's where it comes from. And you can see that the bigger d is, the bigger L perpendicular bar is, and the bigger delta t is, the bigger this is, right? Because the faster it moves, the longer it goes. The longer the length of time you wait, the longer this goes. Okay. And this scales as the square root of time because we're treating in the random walk, we treat the trajectories as straight lines between one time step and the next. Okay. And because we treat those trajectories as little straight lines, over time the random walk is a bunch of little straight lines assembled together to make this random walk. But the longer we make delta t, rather than the length scaling linearly with delta t, the length is getting is decreased from linear by by a factor of the square root of t. Okay. And this is because of treating them as little straight lines rather than the true tortuous path that they would have taken at a shorter delta t. Okay. So hopefully that. Randy asked what happens if there's another surface intersecting with the prism volume for a volume molecular MCell account for that situation. And the answer is the specular reflection accounts for that for us automatically in the following way. So imagine, what if there was another surface up here, kind of cutting through the prism so that we couldn't get the full length, right? Well, because we have specular reflection off of the upper surface, off of all the surfaces, in this volume, we've only accounted for the molecules that move, well, in one time step. I made a slight gaffe in my explanation of this, right? So this quantity here is the total number of particles that are inside this box, inside the prism. So Avogadro's number times the volume of the box times the concentration, that's the total number of particles in the box. But in one time step, half the particles will move up and the other half will move down. But here I didn't divide by 2 because I'm also assuming that there's another prism below this, right? Now, if there isn't, MCell will, in the simulation, MCell knows how you've set things up and will divide by 2 to get the right number of hits for your geometric simulation. Okay, so don't worry about that. But if there's another surface up here, we've truncated through the prism. We can't make a prism that is that big, but what I just said was half the molecules move up and half of them move down. And because of specular reflection, the half that move up will reflect off that surface and come back, right? And the half that move down will hit the surface, and the ones that were moving in the wrong direction move up, but they reflect off the surface and come down. So it ends up being the same amount because of specular reflection. So in the case of volume surface reactions, we don't have to worry about the truncated prism case. But in the volume case, we do have to take into account the truncated volume here for the reasons that I explained here. Okay. Good question. Okay. And I can't see my pointer very well. Okay. Not sure how to make a better pointer. See if I do that, right? I'm not sure how to make a better pointer in Keynote. Maybe there's a way. Maybe.
Okay. Mouse is just fine.
Okay. Okay.
There are 2 more questions from Moritz and Hanya.
Okay. So let's see, Moritz says,
but
you said
actually,
that there's...
my question was just answered. It was basically the same with the prism.
Okay.
Yeah.
Okay. And then Aina says, would you mind explaining again how MCell recovers the probability of collision close to the edge when the surface particles inside the volume, right? So here, right? So this is the case I think you're talking about. So the way we do things here is when the particle is close to the side, or when it doesn't matter where the particle is close to the side. What matters is the cylinder of the diffusing particle has just let's say the particle is just reflected off the surface, and we have the part of the trajectory that's near the surface. So the interaction radius disk, the collision cross-section disk, given by R int, this is in top view, in kind of viewing along the axis of the trajectory. That disk looks like this. We can see that the disk will be truncated by this surface. This black line represents, say, a surface that we're reflecting off of. That MCell calculates the truncated area of the disk and uses the truncated area as the area as the cross-sectional area in the reaction probability equation. So instead of using AET, the full area, it uses the new truncated area to calculate a new probability for the K that we want, in order to then any particles that we intersected at that point would be subject to this collision cross-section area, and that would be the area that we use for asking, do we bind to molecule B or not? Okay, hopefully that was clear. Okay, and thank you. Okay, good. Okay, here we go. Now let's continue. Let's see, and I guess the schedule says I want to keep myself on track here. Let's see, it's 9:23.
Just one more question.
Okay. wondering if it's possible for delta t to be too small so that Newton's approximation on n sub h much greater than 1 breaks down. Well, n sub h has to be less than 1. And I think you mean delta t to be too big. I think John, maybe have it kind of in reverse. So yeah, so let's see, let's go back to where am I here? Go back to here and do this again. Okay, so so Newton's approximation for this quantity is n sub h times pb, but this only works if n sub h is small and pb is small. And so having smaller pb and smaller nh would happen when we have small delta t, and that's a good thing. So there's only a problem when the number of hits is, and it's not n sub h much greater than 1. We just want n sub h to be we want n sub h to be, you know, small. Doesn't have to be less than 1 because we're talking about individual hits here, but it just needs to be a small number of hits. And PB needs to be, certainly PB needs to be less than 1. And that happens when delta t is small. So the problem happens when delta t is large and PB and n sub h are too large. So yeah, so this is a good question, John. So because it lets me say something else that I forgot to say. So so it's true that this approximation works best when n sub h is smaller and PB are small. Maybe PB being, you know, being much less than 1 would be good. But it turns out that MCell is extremely well behaved even when PB approaches 1. So if PB is, say, less than half, then we get about 5%. We get about, you know, only about 5% error when PB approaches half, and when PB approaches 1, we only get about 10% error in the simulation, which isn't too bad. That's kind of amazing. Of course, as soon as PB becomes greater than 1, then it's 100% error, right? It's just wrong because that makes no sense. And of course, if PB is greater than 1, you know, it gets treated as if PB is equal to 1 because it makes no sense for probability to be greater than 1. And so you end up getting what's called missed reactions. And MCell will warn you about missed reactions if PB is greater than 1. And it can happen, especially in volume-volume reactions, because of these collisions. We have to truncate AET, and when particles are when the reflections are close to the surface, we have to adjust AET smaller, right? AET gets smaller, so PB gets bigger, right? Because it's inversely proportional. That can inadvertently make PB greater than 1, but only for the few cases for collisions that are close to the surface. MCell will warn you about missed reactions and give you a readout at the end of the simulation of what % of your reactions were missed. And as long as that percentage is small, your errors are probably negligible. Of course, you can double check yourself when you run your simulations. If you question the result of a simulation, you can always run it again with a smaller time step and see how the result changes. And that's what's called tests for convergence. It's a classic numerical technique that you should always use, even in, especially in ODE and PDE solvers, such as such as you use when you're using BioNetGen language. It's important to do a test for convergence to make sure your result makes sense. Now, there are a lot of good solvers that use adaptive time stepping to kind of offload some of that decision making from the researcher, but it's important to be aware of these issues. Maurice asked, are plans for excluded volume in MCell? Yes, there are plans, and we're hoping to implement those in the coming, in the coming couple of years. We have a new computational scientist joining us from the University of Pittsburgh, Barak Kanak, whose original work was in particle physics in Switzerland at the particle accelerators there. We've been lucky enough to be able to grab him and have him join our team and help us work on this problem. Okay, so continuing. I guess the first break was supposed to be like at 10:30 or something. Trying to.
Yeah, in an hour.
In an hour, okay.
Yeah.
And I think, let me see if I go back here. Yeah, you're looking at this too. Maybe that's okay. Just wanted to see. I said at 9:30 I was going to start introducing the Blender user interface, but I want to continue this for a little bit more. I'll try to pick up the pace a little bit here, because next up I'm going to talk about now using MCell to build a synapse, right? So the title of the talk was how to build a synapse. So now let's build a synapse. So we're going to make a model of realistic synaptic structure in the area of the brain called hippocampus, area CA1 of hippocampus. And we created this 3D reconstruction in collaboration with Kristen Harris. And it's based on a serial section transmission electron microscopy reconstruction of hippocampal neuropil shown here in this picture. Hippocampus, part of the brain in humans, and some nice drawings from Ramon Cajal in the early 1900s. And then here's an EM picture of an area of neuropil and rat stratum radiatum in area CA1. And there's a large apical dendrite in the middle of this field of view. And all the plasma membranes of all the cellular structures in this were reconstructed by hand, by tracing by hand the outlines of all the cells there to create this 3D reconstruction, where yellow are dendrites, green are axons, and the blue is astrocytic glia. And here's showing that segmentation. We also segmented in two of the dendrite segments. We segmented also the mitochondria in magenta and the endoplasmic reticulum shown in cyan. And the synapses were traced as these little red objects here. And here's the 3D reconstruction. I think here the bar in this image is 0.5 micron, and the bar in this image is 1 micron. Scale bar, 1 micron. And if we make the volume semi-transparent, we can look inside and see the apical dendrite going through, and another dendrite nestled next to it. We made all the other axons and dendrites kind of semi-transparent, so we could focus on these two here, one in yellow, one in gray. The little red objects here are the synaptic contacts that had been traced. And we used Blender and Cell Blender to create this 3D reconstruction from the tomograms, and a tool called NeuroPil Tools. That's part of the distribution. Actually, I just lied. I said we used those tools to create this. Actually, those tools were created after we learned how to create this just by brute force, right? And so neurofill tools and Cell Blender were created so that we could better understand this. And we made those tools so that we could do this again easier the next time we wanted to do something like this. But now you could do what I said. We could use it to go back to this original data set and recreate this reconstruction. Okay, so here's that large apical dendrite in isolation with its red synaptic contact areas on the dendritic spines. If we make that semi-transparent, we can look inside and we can see the endoplasmic reticulum and the mitochondria as long spaghetti-like structures rather than the textbook picture of jelly bean mitochondria in neurons. They form these long interconnected networks. And we're going to make a computer model of this, in which we reconstitute what by a process that we call computational reconstitution, reconstitute the function by building up the individual molecules in their locations, in their anatomical correct locations within the 3D structure. So we're going to include AMP receptors, NMDA receptors, glutamate molecules, the snare complexes that control the release of neurotransmitter, voltage-dependent calcium channels, glutamate transporters on the astrocyte. So here's your tripartite synapse, perhaps, and sodium calcium exchangers, PMCA pumps, circa pumps on the endoplasmic reticulum. Missing from this picture is important omission from this picture is that there's also endoplasmic reticulum inside the axon that has circa pumps on it, and the immobile and mobile calcium binding proteins. Here's a mitochondria down here. And we also left out of the model the calcium uniporter on the mitochondria, but we hope to include that in the future. And so all those molecules are implemented in MCell as Markov chain reaction pathways, in which we have ligand-gated ion channels like the AMP receptor, ligand and voltage-gated channels such as the NMDA receptor, whose gating is controlled by glutamate and whose calcium conductance is voltage dependent because of magnesium block. Voltage dependent L and R type voltage dependent calcium channels, whose calcium conductance is voltage dependent and whose state transition rates are dependent on the membrane voltage. Glutamate transporters, the PMCA pumps and sodium calcium exchangers. Here's the circa pump model. And then we model the calcium binding proteins as simple two-state, the endogenous immobile calcium binding proteins as a simple two-state model. And a model like this is also good for modeling the exogenous fluorophores, calcium indicators, fluorescent calcium indicators like FLO4 and OGB1. And also this more complicated mobile calcium binding protein called calbindin, which has this complicated state diagram. And Jim says, are there BNG versions of these models? Yes. And we have BNG versions of these models because Cell Blender can now export the models that you make as BNGL, as you'll see. Okay. So it will make BNGL files from all this. Okay, so there's a few more questions. I'm kind of watching the questions over here. So so this whole dendritic segment is one big mesh. Yes. How do you define the synaptic contacts and PSDs? You will find out. Okay, you will find out. This is what MCell can do. This is what how we handle the meshes in the way we deal with meshes in MCell. This is how we can create things like this. You're going to find out. We're going to make a model today where we make such contacts. Okay. Jim asked, but are they rule-based ones? No, we don't have. I think we have rule-based versions of some of these, but not all of these. It wouldn't be a huge amount of work to do that.
Yeah, I was thinking if there's interest, we could do that in some of our extra time on Thursday or Friday.
Sure, absolutely. Okay, and then Johan asked, is it possible to build such a model without help of experimental groups? Are there any databases available? The answer is no. There aren't any good experimental databases or public databases available with this information that's in a good consumable form. So, you know, there should be, but there aren't. So we go to the literature and we dig the values out of the literature and we build a model. And when the model is done, the model is the database. Okay. So when we publish a model, and we have published this model in Frontiers in Synaptic Neuroscience in 2015, this model is in Cell Blender, and in the way Blender works internally is everything is a database inside. And so that's a good machine readable form, but I'm not sure how, how shareable this is. We can export this as BNGL. There are ways to take BNGL to SBML. So eventually you get into these good machine readable formats, but there aren't really any good databases. There are some, but I don't think they're good, right? So I'm saying any good databases, meaning ones that you can kind of reliably go to and always find what you're looking for there, or maybe not always, maybe that's too strict, but at least half the time find what you're looking for there. Like 0% of the time, you'll find what you're looking for there, right? Practically zero. It's very frustrating. So we're kind of in early days here with some of this stuff. We have these great tools that are being developed, but and I think the SBML community is to be commended for coming up with ways of expressing the models in a way forward-looking so that you could have such databases formed. But I think there is just early days, and there just aren't enough of us practitioners like you guys and us, doing this and filling in these databases. Our biological colleagues, our experimental colleagues who we'd be collaborating with to help us with these models, they're not helping with building the databases, even though they're the ones collecting the data that should end up in the databases. I'm not sure why this is the case. Okay. So, we're left with using our own wits and reading papers and sorting out the good from the bad. Oh, so there's a fun quote from Francis Crick. Had the good fortune of meeting and getting to know Francis Crick in Terry's lab, because Francis Crick was a member of Terry's lab for a number of years. It was great. And one day at our daily tea that we have every day at 3:30, we were sitting around and talking, and someone asked Francis, what kind of models should we make, and should we try to model all the experimental data? And Francis very quickly, wittily said, well, you shouldn't try to model all the data because not all the data are correct. And so this gets at what Miriam was saying. It's very frustrating because, the numbers can vary and some of them are wrong, right? So you have to, we're at the stage now where you just have to use your wits and have your experimental colleagues like Mary Kennedy, who knows the biology very well and can look at something and say, that doesn't make any sense. So let's not do it that way. Okay, so we have in the model that I'm going to show you, we have these kinetic diagrams. Many of these, so if you go to this paper, you'll see the table of all these things and the sources of all the numbers for where these came from. So many of these things are very well known through single channel, ion channel, and kinetic studies. So and all kinds of fluorescent calcium indicator studies and all kinds of things. A lot of these are very well constrained, but some of them are not, and we're going to get to that. Another constraint in the model was this model encompasses pre and postsynaptic. So on the presynaptic side, we have experimental observations of evoked vesicular release from Chuck Stevens' lab over the years. Here's Goda and Stevens from 1994, and the rate of vesicle fusion with the membrane after a single stimulus. And the x-axis is truncated. This is time in milliseconds on the x-axis. I apologize for that. I never noticed that before. And then Dobrunz, Wang, and Stevens, 1997, response to two paired stimuli at different time intervals between the stimuli. The probability of the change in probability of release after a paired pulse. You can see what's called paired pulse facilitation, and then but no depression here. And Chow asks, are the contours tracing for the reconstruction all done with MCell cell bonding? No, the tracings, the hand segmentation is done in Kristen Harris's software called Reconstruct, which lets you hand trace the outlines of things. And then NeuroPill tools that's part of the MCell cell blender suite can take those contours and connect them together into a mesh. And there are some machine vision, machine learning algorithms that can automate some of this stuff, but not all of it. But it's getting better and better. And hopefully that part of things will get easier and better in the next few years. I'm really hopeful and excited about the possibilities there. Okay. And then we are going to simulate the release of transmitter from the presynaptic terminal triggered by the calcium sensor in the snare complex. And we use this kinetic model derived from Schneggenberger and Nair and Sun and Thomas Sudoff, and then adapted by us and published in a PLOS Comp Bio paper in 2010. You can see it's a very complicated reaction network that's calcium dependent binding to the synchronous and asynchronous calcium sensors in the snare complex. The synchronous sensor is site synaptotagmin 2, I think, and the asynchronous sensor is synaptotagmin 9 or something like that, if I get my molecules, my subunits correct. Okay. And then the kinetics of calmodulin and CAM kinase 2. You'll hear more about this from Miriam on Friday, I hope, if there's time. But previously published by Mary Kennedy and Pepke et al., PLOS Comp Bio 2010. Another question. Okay, Anne's answering questions. Okay. Okay, so now, so we have the molecules, we have their reaction kinetics and kinetic kinetic transition diagrams. We have the 3D reconstruction. We now need to put the molecules in their distributions and densities and anatomically distinct locations within our 3D reconstruction. And here's a snapshot of that 3D reconstruction, focusing on one particular dendritic spine and one particular axon and bouton. And here we can see with that, in the axon, we have PMCA pumps on the plasma membrane. We have endoplasmic reticulum with circa pumps on it. We have calcium inside the cytoplasm. We have calbindin that can bind and unbind calcium and buffer the calcium. We have voltage-dependent calcium channels of PQ type. We have synaptic vesicles and snare complexes represented as these little red cones. That's all on the presynaptic side. And on the postsynaptic side, we have AMP receptors and NMDA receptors within the postsynaptic contact area. We have LNR type calcium channels. We have also, not labeled here, but also PMCA pumps and sodium calcium exchangers and LNR type voltage dependent calcium channels. And then inside the cytoplasm, again, we have calcium. There's, of course, calmodulin here in as little magenta guys, and chem kinase 2 monomers here. This is kind of a toy simulation from the point of kind of a first toy simulation of signaling, including the chem kinase 2, but they were represented as monomers and freely diffusing in the cytoplasm rather than anchored near the PSD. So Miriam's project is focused on the holoenzyme and the localization of chem kinase 2 in the PSD. So a much more advanced version of this model that I'm showing here is the focus of Miriam's work. And so these are now going to be the components of the model that I'm going to now show you as a computer animation, showing you this model in action. And the model is going to start from a far away view, and we're going to zoom in on it and get close. And you're going to see the response to a single action potential in the axon. And because there's such a huge dynamic range of time scales here, time is going to progress on a logarithmic scale in 1, 2, 3, 4 decades of logarithmic time. Okay. And here the movie doesn't play well there, so I'm going to open it here and play it for you. Okay. And here's what that looks like. So can everyone see that okay? Yeah, okay. And there's sound with this. I'm not sure if the sound is going to come through and be too loud for you to hear, but it's kind of fun to hear it with the sound. So I'm just going to hit play and try not to say too much about it and just let you enjoy it. Someone give me a thumbs up if you can hear the sound. Oh, no sound. Okay, so I'll just narrate it. I'm not sure why the sound isn't coming through. So as we zoom in here, you can see the axon, and from this distance, you can see the free calcium diffusing in the cytoplasm. That's what 100 nanomolar of free calcium looks like, very, very low. As we get closer, the action potential is going to start. It's going to be indicated by this bright green color of the axon. And the voltage-dependent calcium channels turn from blue to white to indicate that they're opening. Calcium diffuses into the cytoplasm and diffuses over into the active zone where it binds to the snare complexes. And when one of those is bound to 5 glutamate molecules, it releases 2,000 molecules of glutamate into the extracellular space. And the calcium diffuses through the extracellular space and activates AMP receptors and NMDA receptors. And when an NMDA receptor flickers into the open state, it will let in a little burst of calcium like that. And even though the membrane of the dendrite isn't depolarized yet, you still get some calcium coming in because the magnesium block is not absolute, even at depolarized or hyperpolarized potential. But in a moment, there's going to be a backpropagating action potential in the dendrite right now that's going to depolarize activates the CAMK2, and the big blue cubes are the activated CAMK2. Okay, you just saw another release of neurotransmitter afterwards. Sometimes you get what's called asynchronous release of neurotransmitter due to residual calcium left over from the first action potential. And that's what you saw there. It occurs very rarely, but we were lucky enough to get one in this simulation. And as we get now further in time, the PMCA pumps are working very hard to pump the calcium out and out of the dendrite. And eventually things come back down close to the resting state, but that can take several hundred milliseconds. But by 100 milliseconds, it's coming down to a pretty low amount of calcium. Okay, so I'll stop right there and go back into our talk here. And you saw that. And I won't play this again unless people really cry for it. But you know, Terry showed you this on Monday yesterday. And I'll just close with 2 more slides here. Let's come back. Okay, okay, here we are. So from these simulations, we can predict the behavior to several different stimuli. One is when there's an EPSP alone without a backpropagating action potential in the spine. One where there's a backpropagating action potential alone, but no pre-activation of the AMP receptors or NMDA receptors, either because there wasn't an action potential or because there was an action potential, but no release of neurotransmitter. So the one thing I didn't say is in these synapses, the probability of release on average for an average kind of synapse is only about 20%. So 80% of the time when there's an action potential, there is influx of calcium into the axon, but no release of neurotransmitter. So it's a curious thing. And this is the basis, this is part of the basis of synaptic plasticity, because that release probability is adjustable by learning. And then finally over here, what things look like if there's an EPSP first and then 10 milliseconds later, a backpropagating action potential. And the take-home message here is that the NMDA receptors that are responsible and the voltage-dependent calcium channels that are responsible for the influx of calcium into the spine are highly stochastic in their behavior because they're ion channels that flicker open and close, and there's only a few of these ion channels present in the spine. There's only about 10 NMDA receptors total, and on average, only about less than 1. On average, right? There's a lot of zeros in here. So if I average this out, it's actually way less than 1 channel open, or its duty cycle is so. You have to talk about these things in terms of like digital information encoding, like pulse width modulation or pulse coded modulation, where there's a certain uptime and downtime and a certain duty cycle to the signal. And, it's not at all continuous. And notice here in this bottom row down here, we have the calcium concentration in the spine. These are individual instances up here. So black is one instance, and the gray are the other trials superimposed here. And here the blue is one trial, and the gray are several other trials superimposed on here. And so this is the average of about 100 events. If I put in one event, it would be just as noisy as this. But if I average 100 together, notice the difference in scale on the y-axis as you compare across this bottom row. The one to pay attention to, I think, is the black here, which is the case with calbindin. and the red one, the case with calbindin, and the blue one, the case with calbindin. We have without calbindin here because in experiments, when people do their whole cell clamp experiments, when they clamp onto the cell, they wash out the calbindin from the cytoplasm. And so the experiments that are reported in the literature are best compared with the case without calbindin. And notice how with the EPSP, we get a much larger and longer lasting calcium signal in the dendritic spine when we pair these together, when the EPSP and BAP are paired together. And the other part of the model is a point was made that how much of this is how much of these kinetics are known from the literature, and a lot of them are known, but some of them are not known. And so to build the model, what we did was we calibrated it against experimental measurements of the calcium signals in dendritic spines. And that's, come on, why is this giving me such a pain to advance? It's having trouble advancing to the next slide. I think it must be, yeah, okay. So there was a seminal paper published by Sabatini, Svoboda, and Ortner in the year 2002 entitled The Life Cycle of Calcium in Dendritic Spines, in which they reported their very detailed imaging studies using fluorescent calcium indicators in dendrites, reported the properties of the calcium dynamics in dendritic spines after stimulus. And so the results of their paper are shown in blue for different amounts of exogenous calcium indicator added to the cell in their whole cell clamp setup. And so what they were trying to do was estimate what's called the endogenous buffering capacity. And this is done by taking these blue dashed lines and extrapolating back to 0 exogenous calcium indicator. And that gives you a value for kappa B. We didn't really care about calculating the value of kappa B. What we cared about was making our simulation match their experiments. And so what we did was we kept everything fixed in the simulation that was well constrained and known, and varied things that were unknown. And we varied basically 7 different things: the density of PMCA pumps, the amount of immobile calcium binding protein, and the rate constants of the immobile calcium binding protein, and several other factors that I'm having trouble remembering. We varied these 7 unknown parameters independently to try to get a simultaneous fit to these basically these 9 experimental measures, or these 4 lines, right? And the lines have a slope and an intercept. So there's like 6. You take these lines as a slope and an intercept, and we have 6 experimental values, and we adjusted 7 or 9 different parameters in the model. So we were kind of over determined in our model, but we were able to find a unique fit that pretty well fit their experimental results. And what's cool is after adjusting those parameters and getting these fits to the case where we have the calcium indicator included in the model, we could then ask the question, how that was a burning question that Terry mentioned yesterday, a burning question of Erwin Nair that he asked the Pope. What are the, that Erwin Nair said that he would like to ask God, what are the calcium indicators and what do they do? Well, we kind of sort of have an answer to that, to a good part of that question here. And a burning question that people have had for a long time about these calcium indicators is that by putting in a calcium buffer, basically the indicators are a buffer. And by putting a buffer into the system, you're actually changing the base behavior of the system. So, it's a classic thing in science that, in order to observe something, sometimes you have to perturb it, right? In order to observe it. But when you make the perturbation to the system, how do you know the effect of your perturbation? And in the case of these calcium indicators, you can't really know the effect of your perturbation because you can't see what happens when the calcium indicator isn't there, except in computational modeling. We can't. So that's what's illustrated here. So their calcium indicator gave them a signal that looked like this red curve. And the reason why it looks like this red curve is because it's and not like this green curve is because they can't sample at high enough sampling rate in order to see the rapid transient part of the signal. They're by sampling in time, they're actually severely low pass filtering the signal. But you can see that when the signal is changing slow enough, then yes, their imaging apparatus with sampling the photons does have enough frequency response to track the slow part of the signal transient. So that so that's kind of proof there that that there is a correspondence between what they observe and what's really happening, but only at very slow signals. And so we can, in our computational experiments, we could show that they're missing this transient part of the curve in when the calcium indicators are present. And this is for a small spine. And for a big spine, it's even a little bit more extreme what they're missing in the transient part of the signal. But then we could do something that they couldn't do, which is show what happens when you have no calcium indicator at all in the system. So that's indicated by the blue curve here. You can see that they're great, the indicator is greatly changing the behavior of the system, greatly perturbing the system. And more so in the small spines than in the large spines, but it's still greatly perturbing the system. Okay, and with that, I'll close my talk and we'll start the hands-on part of the of our work today. But I just wanted to acknowledge, this army of people who we've been so fortunate to have, and collaborate with over the years. Okay. So before I keep going, let's maybe have a few more questions. Let's see. So, okay, so a few questions. Someone asked, Michael asked, what happens to the action potential? Where does it go? Well, so the action potential is a traveling wave that is traveling down the axon. And what you saw in the simulation was such a small piece of space, a short piece of space, only about 5 microns wide. Our field of view there was only, well, after we zoomed in, our field of view was only maybe 1.5 or 2 microns wide. The velocity of the action potential is so high relative to that scale that you don't see the wave. What you see is it is just an increase and a decrease in the amplitude of the voltage at a single point in space, but it's actually traveling at, I think, something around 1 or 10 meters per second, depending on whether it's myelinated or not. I think in unmyelinated axons, depending on the diameter of the axon, the velocity is between 1 and 10 meters per second. And in large myelinated axons, it can be 100 meters per second, the velocity of the action potential. Okay. Okay, so now at this point, it is about 10 after, and I think we had said that there'd be a break at 10:30. And let's see, I'm going to change my screen layout back to normal. Oh, that's not what I wanted. I wanted displays and arrangements and not mirror. And okay, everything's now back to the way I like to have it. Close that down. I'll put this there, that up there. All right, just give me a second. Okay, I'm arranging all your nice faces on the screen. Okay, so if anyone has a question before we continue, now's the time. But let's take, before the 10:30 break, let's take 20 minutes to have a quick initial look at Blender. So let's see, I'm looking for my screen here. Let's see, where is it? So I have a bunch of virtual desktops, as you see here. All right. I like keeping my work compartmentalized. Let's see. Probably this one's good. Yeah, this is the one I want. Okay. So if you have Blender installed, there's a couple different ways that you could fire up Blender. But there's a preferred way to do it. But let's see, one way to do it is, to find your Blender app and double click it. And if we do that, at least on a Mac, it's going to give us a problem. But I want to show you on a Windows machine, it might not do this, or on a newer version of Mac OS X, it might not behave this way. But it's going to say it doesn't like it because it's damaged. Well, it's damaged because we have added things to it that aren't recognized by Apple as being officially part of the Blender release. And so there's a certificate code that was put into Blender by the app developers that verifies that it's not, that it hasn't been hacked or corrupted by somebody. But of course we did hack it a little bit, and we didn't have a way of changing the certificate code. So the Mac is going to complain about that and say it's corrupted and you should throw it out, but don't do that. So the other way to run Blender would be to find on the command line, is to go to the command line. And if you went into applications and the Blender 293 Cell Blender directory. When you look at it from the command line, the Blender app looks like a folder. The little slash after it means it's a folder. And if I CD'd inside there, then I can see the contents of it. And there's all kinds of content in it. And inside this Mac OS X subfolder, there's actually a Blender app. I mean, a Blender executable. And so I could run that Blender executable, right? And it fires everything up, and then I get Blender. But I'm going to quit from this just for a moment and show you that at the top level of the directory where we've distributed Blender, the Blender Cell Blender distribution to you, at the top level of that is a script called My Blender, which makes running it much easier. Instead of having to CD all the way down into that directory or knowing that path, instead of doing that, you can just run My Blender. And there's some shortcuts to doing this, but I'm just going to go back to my home directory. And what I can do is on the command line is I can type this and then say My Blender like that. And then what I like to do is put an ampersand at the end of the command. If you're on Linux or a Mac, you're using the Unix operating system, and so you can run a command and put it in the background so that I still have control over the terminal window by putting the ampersand there. You don't have to do that though, so let's not make things too complicated. Leave that off. On a Windows machine, you can probably just double click on a Linux machine and a Windows machine, you could probably click on the icon and it would come up without complaining. But if you did that, then you wouldn't get the benefit of some of the text messages that are going to be printed out by MCell and Cell Blender as it runs, that are sometimes helpful and diagnostic things to have. So even on Linux and Windows, you're probably going to want to use a script, a scripted way, or use the command line as the place where you're going to fire up the tool. Okay, so I'm going to now, type in the path to the My Blender script and hit enter. And it prints out some diagnostic things that we won't look at right away. And when it fires up, you'll get this splash screen, which you can just, and inside the splash screen will be recent files. And so anything recent work that you've done will be there, and you can click on something and it would come up, but I'm not going to do that now. We're just going to go straight into Blender to get a quick tour of the user interface. So click outside the splash screen, and this is what you're going to see when you go into Blender. And if you have a 3-button mouse, which I hope you do, things will be easier for you. A real 3-button mouse. If you look at my image, a real 3-button mouse with a scroll wheel on it is even nicer. Then things are going to be easier for you. And if you have a real, a real keyboard with, because Blender has a lot of functionality and hotkeys on the keyboard and different uses for the different mouse buttons, it's going to be easier to use if you have, a real keyboard and a real 3-button mouse. But if you don't, the user interface in Blender is customizable so that you can make use of your trackpad in a way that's compatible with a 3-button mouse. So if anybody is using their trackpad, and doesn't have a 3-button mouse, maybe type in the chat window, and I'll show you some tricks for getting around that. But okay, so in the 3D view window, by default, when you first come into things, you'll see you have a cube object. That's kind of like your lump of clay. If you're a sculptor in your studio, you might have a lump of clay on a table in the middle of your studio. This is like the computer graphics artist's lump of clay right here. Okay, and then you'll also have a camera and a lamp. So if you're a director of a play, another way to think about this is like the stage of a play, and we need lights, and we need cameras, and we need action, right? And the action is carried out by the actor, and the actor is your CG, the subject of your CG movie. In this case, the cube or lump of clay. And of course, the scene, the scene on the stage, is on the stage floor, which often has marks on the floor so that so the actors know where to stand during the play and how to move during the play. So this might be what the director sees looking at the actor and the cameraman and the lighting grip. Okay, so now if I'm the director looking at my scene, I want to move around the scene and look at it from different angles. I can use the middle mouse button on my 3-button mouse and click and drag and rotate the scene and rotate myself, basically move myself around the scene, rotating like this. Now, if I use the middle mouse button again, the scroll wheel, and scroll in and out, I can get closer or farther away. And if I middle click, let's see, how do I do? And if I shift, I'm sorry, hold down the shift key on the keyboard and middle click and drag, I can kind of walk side to side across the screen or move myself up and down. Now I'm like a drone. I'm a cameraman. I'm the director, and I'm sitting on a drone, and I can move my drone around the scene like this. Okay, so those are the basic tools for manipulating. And if I left click, what I was doing here a moment ago was left clicking on these. If I left click with the mouse button, then I can select these different objects. And if I click outside of an object, then I've unselected everything. So clicking outside of things unselects. If I don't click on anything, then I've unselected everything. Okay. And if I want to select everything, I can shift click one at a time, like this. I can shift click, and again, if I click outside, I unselect everything. But what if I have too many things to click on? What if I want to select everything in one smooth motion? Well, the A key on the keyboard selects all. And to unselect, you just click outside. You can also double click the A key, but I found that can sometimes be unreliable if you don't double click fast enough. So, the quickest way to do it is just to left click outside of everything if you want to unselect everything. Okay, so that's the basic navigation of the scene. Now, there's a lot of other things going on here that we could talk about, but what I've just showed you is pretty much all you're going to need for navigating and understanding the scene for the tutorials that I'm going to show. And I'll leave it to you guys to educate yourself more about Blender using the Blender tutorial on blender.org. You can go and find all kinds of Blender tutorials on the amazing things that you can do with Blender, which are really too numerous to discuss, but leave it, suffice it to say that Blender is really a state-of-the-art computer graphics creation suite that can be used to create feature-length, Hollywood quality animated feature films. You really could, and it was invented by practitioners who are using it to do just that. And it really is state of the art. With the latest version of Blender, it's now very highly respected and recognized within the CG cinematic community as being as good and sometimes better than some of the really expensive tools made by Hollywood CG companies. Okay, but why are we using it? Why are we using it? The reason why we're using it is because doing stuff in 3D is really hard to do. We're making models that are going to have realistic 3D geometries or any kind of 3D geometry. As soon as you're in the world of 3D, it can be really hard to work with unless you have a good tool that makes things easier to do. And Blender for us is so good, it really is that tool for us. Okay, so now let's go to the next stage of what I want to show you. So there's a few setup things in the interface that will make things more convenient for us. So we're going to go to the Edit menu, and we're going to go to Edit Preferences. And there's a few preferences that I want to turn on because a few options in the preferences that I want to turn on because it will make things easier for us. So one thing I said was we could emulate a 3-button mouse if you don't have a real 3-button mouse. And you get to that under the preferences under this input tab, and you just click on emulate 3-button mouse. And you see that I have that turned on, even though I have a real 3-button mouse. Also, this is on my Mac. So when I unplug the mouse, I'll still be able to do things on the trackpad on my Mac. And Blender's smart enough to know that when I when I have a real 3-button mouse, it'll do the right thing, and when I use a trackpad, it'll do the right thing. So you can, if you want to be safe, you can even just turn that on. Okay, now let's go to the interface tab at the top, and what we're going to do is we're going to turn on developer extras and the Python tooltips, which will probably be turned off on yours. And these are going to be useful things for maybe not during this workshop, but for later when you want to start customizing and making your own Python scripts in Blender. Having these developer extras and Python tooltips turned on can be really helpful. And then the other thing is if you go down to the status bar, which is collapsed, status bar option, which is collapsed, click on the little triangle to open that. We're going to turn on scene statistics and system memory. And what this does is if you look down in the lower right-hand corner of your screen, you'll see there's an area down here which just has the Blender version number listed, 2.93.1. But if I turn on screen statistics, it's going to tell us that our scene contains 8 vertices, 6 faces, and 12 triangles, 3 objects, and 0 objects are selected. And also, if I turn on system memory, it's going to tell us how much computer memory that our scene or Blender is currently using. And I find that these are useful things to have around as we're creating our scenes and making objects, it's useful to know what we're looking at. And if I want to be sure that only one object is selected, because what if, what if I have two objects selected here, right? But I pan off to the side like this, and I can only see this one object. How do I know when I click on this, how do I know there's only one object selected? I look down here and I can see it says one object selected, right? But if I had that one also selected and move this off to the side, I'd only see this, but it would say, oh, it looks like one object selected, but no, there's two objects selected. Okay, so that's useful. Okay, so back into the preferences again. So we're going to turn those on. And then in navigation settings, I like to have this mode called trackball mode turned on. So right now we don't have trackball mode turned on. And what that means is when I go into the scene and I rotate, I can only rotate up and down and side to side. Let me bring this back to bring that back to the center again. Yeah, there's some other hotkeys I'll teach you about in a second. So, I can only move up and down and side to side. What if I want to tilt? What if I want to tilt the world like this? I can't really do that easily with turntable mode. And turntable mode is useful if you're doing some mechanical thing, designing some mechanical thing that has a well-defined up, down, and front and back and left and right, but that sits on the floor. But we're working with biological things that have no real set, geometric orientation to them. So it's more useful to have trackball mode. So we're going to turn on trackball mode. And in trackball mode, now I can move up and down and left and right like before if I'm close to the middle of where the object is. But if I go off to the side and I click, I can rotate the world. So it's as if there's an imaginary sphere, trackball, right, around the world. And by grabbing on that trackball in different places, I can move that imaginary ball around. Okay. So I like trackball mode. And then the last thing, which I think is really important to turn on, is in the System tab, this feature called Global Undo. So this makes Blender use more memory, but I think it's worth it because it lets us really be able to undo anything we have done that may have been an accident. If we accidentally do something, this is the best reliable way to undo. Okay, so global undo. And that's it. Autosave is already turned on and all kinds of other things are all here. You don't have to worry about them. So I'm just going to leave them the way they are. Leave those settings the way they are. Okay. And you don't have to save the preferences. They're automatically saved. Okay, so now with that, we're at 10:30. I'll maybe show you one more little piece of user interface, and then we'll take our 10:30 break. Okay. Oh, Lenka says one useful tip was to also tick depth in navigation. That could be useful too, but let's just leave that alone for now. Okay. So the other thing, the other hotkeys on the keyboard that I want to show you is if you have a numeric keypad, which you should, there are some nice hotkeys. If I've moved the scene somewhere and I get lost, if I hit Shift-C on the keyboard, that recenters the world back to kind of the default view. Except it's not really let's see if I do this and move that off to say, you see that was rotated. If I hit Shift-C, it comes back so that the whole scene, its objects are all, centered in the view, but it's not really the home screen. It's really just centering it with whatever, rotation you've already got. If I push this down like that and hit Shift C, it comes back. So I can see things. Okay, so Shift C is good. But what if I really want to center the object that I've got? Like if I rotate this way off here, now when I rotate, I'm now rotating about, some imaginary thing here in the middle here. What if I want to rotate the world about the camera? If I click on the camera on the numeric keypad, if I hit the decimal key, the dot key, it now centers the camera and makes the camera be the center of rotation. Now the camera center of rotation is this apex at the end of the frustum of the camera. And so now I'm rotating about the camera. If I want to rotate about the cube, I click on the cube and hit dot, and it zooms in on it. So when you hit dot, it zooms in on it and centers it. And if I just, zoom in and out, now it doesn't move, doesn't change the center of rotation. I can now, rotate about the camera. Okay, so that's the dot key on the keyboard. Another useful thing is on the numeric keypad, the 5 key toggles between, if you look up here in the upper left-hand corner of the screen, it says user perspective. If I hit the 5 key, it says user orthographic. So this shifts between perspective mode and orthographic mode. And if you're making models that have to be dimensionally correct and constrained, and you need to make really fine judgments about the sizes and dimensions of things, it's best to be in orthographic mode. Okay. But of course, perspective mode gives you kind of the most realistic, view, as if you were, had binocular vision and you're looking at this, right? Okay. Perspective, that's hotkey 5. And then the other, 3 keys on the numeric keypad that are really useful are the 1 key. And the 1 key gets you a top view. Is this a top view? No, this is which way is the top view? 7 key. The 7 key is the top view. And we know it's the top view because if we look in the upper right-hand corner, we get, Z, X, and Y. So Z is coming up. So this little widget up here is kind of like a little virtual coordinate system. You can see there's it's what's labeled on it is the positive X, Y, and Z directions. These are what's labeled here and have the little axes drawn on it. Okay, those are the positive X, Y, and Z coordinate system. And if I hit 7 on the numeric keypad, you can see X is to the right, Y is up, and Z is coming up out of the page toward us. And you can see the grid gets really kind of cool to look at when you're like that. And if I were in perspective mode, 5 key, you can see the perspectives, there's foreshortening of things in the distance, right? And so the 7, so that's why I like orthographic mode for most things. The 7 key on the keyboard gives us the top view. The 1 key on the keyboard gives us the front view. So that in the front view, X is to the right, Z is up, and minus Y is coming toward us. So if you look on there, you can see it says minus Y. And if I hit the 3 key on the keyboard, this is now the view from the right side, because positive X is coming toward us. Y is to the left, Y is to the right, and Z is up. So this is a view from the right-hand side. So we have 7 is top, 1 is front, and 3 is from the right side. Okay, of course, from any of these views, I can just start rotating with the middle click on the keyboard, middle mouse button, click and drag. Okay, so let's take our break if it's okay with you guys, let's make it be a 20-minute break instead of half-hour break and come back at 11 so that we can stay on track with our schedule. That's okay. And when we come back, let's see, the schedule says that it'll be a new
Yes.
Zoom link. Oh, and I think it says, yeah, it says 10:45, right? But let's,
Let me double
yeah,
check.
I guess the break said 10:30 to 10:45, 15-minute break.
If you want, we can just come back around like whatever 11.
Yeah. So let's come back at 11 to make it a nice.
So then let me correct this link 40 and then make this one 11, and please use the new link. So
Yeah, when we come
okay.
back. Okay. And we're a hair behind, but not too bad.
Yeah, it's not bad at all. Thank you very much.
Okay.
Thank you. So
Okay.
I'm going to close this session. Is that okay for everyone?
Sure.
Okay, so I will close this in some like five
Okay,
seconds.
we'll stop sharing and we'll be right back.
Perfect. See you.
Give you guys a chance for your brains to cool down a little bit.
Yeah.